Namaskar, good morning, good afternoon, good evening, depending upon which part of the world you are. आप सभी का PRL का अमृत व्याख्यान में स्वागत है, अभिनंदन है. Very hearty welcome from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान. This is the 9th व्याख्यान of the 75 episodes series of Vyakhyans, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space science. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee, that is PRL at 75, coincides with India's 75 years of independence. So it's a joint celebration of development of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today's Vyakhyaan is being delivered by another great scientist from Japan, Professor Kazuo Shiokawa. And this Vyakhyaan is a unique one in the sense of that the title of this Vyakhyaan is Dynamics of Aurora and Airglow in the Upper Atmosphere and the Space Science Around Earth. As we all know, PRL is well known in the field of astronomy and space atmospheric sciences for decades. It's essentially the development activities at PRL which led to exploration of upper atmosphere and ionosphere at Thumba using the rockets where the first instrument flown were developed in PRL. So PRL has a legacy of working in this area for several decades. With this, I would now request my colleague, Professor Pallam Raju, to introduce the speaker. Over to you, Pallam.
Thank you, Professor Bharadwaj, for the welcome address. And it's really an honor and great pleasure for me to introduce a distinguished scientist and a great friend, Professor Kazuo Shiokawa, to this audience here. Professor Shiokawa is presently the Vice Director of the Institute of Space, Earth, Environmental Research in Nagoya University in Japan, and currently the Director of the Center for International Collaborative Research at IC at Nagoya University. He is also the elected President of the International Council for Science body, which is COSTEP, Scientific Committee on Solar Terrestrial Physics. And under this program, the present Presto, a big international program is underway, which under the auspices of COSTEP. Professor Shiokawa did his BSc and MSc from in geophysics from Tohoku University in Japan and PhD from Nagoya University. He had worked as a research associate at the STEL, Solar Terrestrial Environmental Laboratory at Nagoya University, and a visiting scientist at Max Planck Institute for Extraterrestrial Physics, Germany, and associate professor at STEL in past several years. His research interests include space sciences and astronomy in general, and in particular the dynamical coupling in the various aspects of solar wind, magnetosphere, ionosphere, thermosphere, mesosphere, and also in terms of building ground-based optical and electromagnetic measurements related to aurora and airglow. Professor Shiokawa has received many awards and recognition, which include Obayashi Early Career Scientist Award in 1999 and Tanaka Date Award in 2009, both of Society of Geomagnetism and Earth, Planetary and Space Physics. He has received excellence in review and refereeing from JGR Space Physics. And in a couple of years, 2010 and 2011, he's a member of the Society of Geomagnetism and Earth Planetary and Space Physics, Japan, the AGU, the American Geophysical Union, and the Meteorological Science Society of Japan. He has published over 320 articles in peer-reviewed journals, in addition to several chapters in books. Today, he's going to talk to us on the dynamics of aurora and airglow in the upper atmosphere and space around the Earth. So with this few words, I will now invite Kazuo to deliver his the ninth Amrut Vyakhyaan, PRL Amrut Vyakhyaan. Professor Shiokawa, please.
Thank you very much for very nice introduction, and congratulations for the 75th anniversary of the PRL. It's a really a long history to develop the physics, particularly in this field. So today I'd like to talk about the dynamics of the aurora and the airglow in the upper atmosphere and space around the Earth. The first part is about aurora, and second part is airglow. My point is that both phenomena, aurora and airglow, visualizes the various dynamical variation in space plasma and the atmosphere. So I can show you the this visualization of the dynamics of this space around the Earth. First, this is photographs, movies taken by, from the International Space Station. You see the aurora in the higher latitude, which is shown as green and red, and it shows various motions. And as the space station goes to the lower latitude, you still see some green light emission. That is so-called airglow, which covers around the Earth. So as you see, the aurora moves dynamically and changes its shape in time, and sometimes it pulsates like this. This is a photograph of aurora, which I took a long time ago in Svalbard, Switzerland. The aurora shows mostly the green colors, and it shows this kind of complicated structures. And if you go at the below to the aurora, it is like a radiative structure, which is basically the structure of the geomagnetic field of the Earth, because the particles precipitate along the geomagnetic field. And in many cases, aurora shows a vortex-like structures like this. This indicates that plasma around the Earth in space is also creating a vortex flowing around the Earth. And the aurora visualizes that situations. This is a photo in Canada when it is very strong geomagnetic activities. The aurora is not only the green, but also it's red, or it is mixed into yellow and very active. Sometimes we can see this kind of patchy-like aurora. Compared to the previous aurora curtain-like structures, this aurora is more like a cloud, and we call it patches. And in most cases, this patchy aurora pulsate on and off. I mean, the aurora emission comes, and 1 second later it disappears, and 1 second later it comes out. So it oscillates the emission. This is the so-called pulsating aurora. So I show the movie of the aurora, which I took a long time ago in Katzville, Alaska, and which indicates the so-called auroral substorm. This is when I was in Katzville in Alaska in 1994. We took the aurora images using a video. The time is about 20 times faster than the real time. And this is all sky images. The top is to the north, and the bottom is to the south. Right is to the east, and left is to the west. Now you can see in the northern sky, there is a east-west auroral curtain, auroral arcs. We call this auroral arc. And now the auroral arc is slightly brightened and comes to lower latitude, gradually coming to southward. And another brightening happens and weaken. Another brightening. And there are some motions. And it's split into two regions. Then the next brightening comes from the east. And then the final brightening comes from here. And now the Aurora substorm started. And after the substorm started, the very active aurora covers whole sky. Then you see the patchy aurora, as I said before. They are cloud-like auroras, and it pulsates, oscillate on and off, with slightly changing its shape. And then the auroral intensity gradually decreases and weakens. This is about 1 hour phenomena, which is called auroral substorm. And this kind of substorm often occurs at least once a day. So aurora is not a stable phenomena, but usually it is stable, but once or twice a day, it becomes suddenly active and covers whole sky. That is called auroral substorm. Now let's think about the location of aurora. This is auroral images from the satellite. You see the aurora in the northern part, and this is a Japanese island. You see the big city, Tokyo city light, and Osaka, Nagoya. I'm here, Nagoya. And aurora is usually in the north, very north, far north, and over the eastern northern coast of Siberia. So it is at the high latitude phenomenon. And if you further go outside view, this left panel is the auroral view in the ultraviolet images by the NASA's polar satellite. You see the aurora is at latitude around 70 degrees. And if you see the detailed structure in the visible wavelengths by the GMSB satellite, that is more complicated structures inside of this. This is a different time images, but in the ultraviolet images, it is difficult to see the detailed structure. But in the visible images, you can see more detailed structure. And when we look this from the ground station, you can see this curtain-like aurora. So aurora has a globally the ring-like shape surrounding the North Pole at around 70 degrees. But inside of that, there are many small-scale structures. So this is just a cartoon. Aurora is surrounding the North Pole like a ring. So if the some creatures from outer space come to the Earth, they will see that the Earth will have two rings in the northern hemisphere and southern hemisphere. It's so beautiful. And the aurora is not only on the Earth, but also on the other planets. This is the aurora observed in Jupiter, observed by the Hubble Space Telescope. And you can see the northern polar region and southern polar region, the aurora appears like on the Earth and surrounding around the North Pole and South Pole. And this is an expansion of the North Pole region and like a ring-like shape around the North Pole. But you also notice there's a spot-like aurora. This is so-called EO-related aurora because the Jupiter has several satellites. One of the satellites is called IO, and that has an atmosphere and a volcano. So the EO's atmosphere mainly from the volcano gas move along the magnetic field line and make this aurora and with the tail. So this is a very interesting structure, particularly in the Jupiter. In case of Earth, we have a moon, but the moon does not have atmosphere, so we do not have a moon-related aurora. But in case of Jupiter, Io has an atmosphere, so it can create these kinds of spot-like aurora. Okay. Now I talk about some basics of the aurora and the airglow height. So the height of the aurora and airglow, aurora is about 90 to 600 kilometers from the ground level. And the airglow, I'll explain later, but it is about 80 kilometer to 100 kilometer, and another emission comes from 300 kilometers. This altitude is very high, and the highest mountain is 8,000 kilometer Everest, which is 8 kilometer. And the airplane is flying around 10 kilometer. So the place around 90 to 600 kilometer is where the low altitude satellite or International Space Station is flying. So Aurora region, where the emission comes from, is the where the satellite, most of the satellite is flying over. So in that sense, the investigation of aurora also corresponds to the investigation of the environment around the space station or satellites. The Earth radius is about 6,000 kilometers. So the aurora height is 600 kilometers. So the aurora is still on the surface of the Earth. Now, how the light emission occurs. In this very high altitude, like 90 to 600 kilometer, it is like in space, because space station is also flying. But it is not a complete vacuum. But the Earth's atmosphere is still somewhat staying here. So the emission comes from the Earth's atmosphere. Actually, the Earth's atmosphere, air, atoms, and molecules, roughly speaking, it is composed by the atomic core and the electrons around that. And if the some particles from particularly the electrons from space, or in case of airglow, the solar UV emission, ultraviolet emission from the sun hits the air molecule, then this electron gets the energies and start to move around the outer shell of the these molecules. But this station is unstable, and in a certain lifetime, they come back to the original state or other states. And at that time, the energy difference creates the optical emission of aurora and airglow. So the aurora and airglow is mainly coming from the air, atmospheric atoms or molecules, which is neutral particles. But it is excited by the space plasma or solar UV emissions. And the interesting point is that these molecules or atoms has several different states, and that energy difference corresponds to the color of the energy state. So by measuring the color of this aurora, you can estimate energy, exciting energy of the these auroral source particles. So because this structure has a fixed energy difference, aurora has a fixed color. This is a spectrum, color spectrum of top part is aurora, and the bottom part is a solar spectrum, the sun. The sun has a continuum emission from blue, green, yellow to red. Aurora also has a various spectrum from blue, yellow, green, yellow to red, but it has a so-called band spectrum or line emissions. It has only a fixed wavelengths to emit. So by measuring these wavelengths, the people in 100 years ago, they measure what kind of molecules or ions exist in the upper atmosphere. So for example, when the low energy electrons precipitate, we can expect the high red emission at high altitude. And when medium energy or higher energy electron precipitate, we can expect green emission at lower altitude. So this indicates that this is a low energy and medium energy precipitate to the Earth simultaneously. And more active case, when the aurora becomes like substorm after the substorm breakup, the bottom side of the aurora becomes pink. And this pink color is from nitrogen molecule. And this is highest energy, like several tens of kilo electron volt electrons causes this nitrogen molecules. So by looking at the color of the aurora, we can roughly estimate the energy of the precipitating particles. Okay, so these particles are from the geospace to cause aurora. It is called plasma. Plasma is the molecules or atoms which has a space charge, positive or negative charge. They call it plasma. So the plasma hits the atmosphere, then the aurora emits. Then where the plasma comes from? So the plasma is mainly coming from the sun. Okay, you may think about that the space around the Earth is completely vacuum, but it's not true. If the some creatures coming from outside galaxy, they feel that the space around the Earth is filled by the plasma, and that plasma is mainly coming from the sun, because the sun has an atmosphere. Sun emits plasma to the Earth. So compared with the outer galaxy, we have a dense plasma around the sun, and the Earth is in the dense plasma ocean, and it is protected by the magnetic field. So let's think about the sun. The sun is like a yellow ball, but if you look into these details of the solar surface, you can see it is not a stable yellow ball, but it is actively moving. This is a collision of the sunspot, and you see it is like a fluid and moving around. So sun is covered by the plasma, mainly from hydrogen or helium, and it also has a magnetic field. So if you see the sun from the X-ray, which is a higher shorter wavelength emissions, the solar surface is not stable, but you see many detailed structures, and this is near the sunspot. You have an active emission of the X-ray, and this is a movie. So the sun is rotating with a rotational period of about 27 days or a month. And during the rotation, they change its shape, and the actively this stuff is moving around. So sun is always active, and many volcano-like plasma emission is coming out. And when you see the sun from a bit far away from that previous telescope, and this is a Soho-Lascaux coronagraph, the sun is in this white circle. Because sun is too bright, we put the black metal plate to avoid the strong emission of sun, and we see only the solar atmosphere outside of the sun. And here you can see the sun is emitting the white emitting plasma outward like this. So I move the movie. So again, the sun is not stable and emitting the plasma always outside. And the Earth is in this plasma ocean from the sun. And this plasma ocean of the sun is not stable. And the plasma flow from the sun changes its intensity like this. Sometimes the big eruption happens, and eruption when the eruption hits the Earth, we can have geomagnetic disturbances, like geomagnetic storm. And as you may know, the solar activity changes in longer time scale, like 11 year. The most famous solar cycle is a 11-year solar cycle. This is a recent solar cycle, cycle 20, 21, 22, 24. Now, in 2021, we had almost minimum activity of the sunspot and the solar plasma emission. But still, the sun is emitting the plasma continuously. And for longer term, in the top panel, this is 400 years sunspot numbers. As you see, there's a clear 11-year solar cycle, but the activity changes in time, and it's not stable. Like recently, we have a very high activity, but the previous years there are minor small activities, and around 1600 to 1700, there's about 100 years of no sunspot numbers. So the solar activity is also not stable, and it changes in long term. And interestingly, there's a correlation between this solar activity changes and the ground surface temperature. This is a paper by Dean et al. In the top panel, the solar activity, and second panel shows the solar irradiance, total irradiance, which is about 1300 watt per square meter. This is a solar constant, 1366 watt per square meter. And as you see, this solar irradiance changes in time for recent 400 years, and there's some correlation with the sunspot numbers. So the solar related to the solar sunspot number activity, the solar irradiance reproduced from several ways, they also changes. And the bottom panel shows these two lines, a solid line and dashed line indicates the temperature of the Earth, and this total solar irradiance. So there's a correlation between the Earth's temperature and the solar activities, like this. And the most recent one, 50 years, the surface temperature significantly increases. This is an anthropogenic effect, human effects, and this causes a serious global warming, climate change. But before that, there's a good correlation between the solar activities and the surface temperature. So what makes this high correlation between solar total irradiance and temperature on the Earth? Now, the solar irradiance variation is only 0.1% from the total solar irradiance. Total solar irradiance is 1300 watt per square meter, but the variation is only 0.1% of that. And we know that this small variation cannot create this large temperature variation on the Earth surface. The temperature variation is about 0.5 degree in this time. So this solar irradiance variation cannot explain this temperature variation. Then there are several other nonlinear models that can possibly cause the climate change or temperature change on the Earth. These are some models. One idea is that the galactic cosmic ray changes the cloud concentration and cloud changes the surface temperature. And galactic cosmic ray is controlled by the solar magnetic field intensity. So in such a way, the solar magnetic field intensity, solar activity may control the surface. But recent laboratory experiment may deny this idea. And the other is total solar irradiance may change the sea surface temperature, and sea surface temperature may control the climate. The other idea is the solar UV emission. Solar UV emission variate much larger, but it is mostly absorbed by the ozone layer in the stratosphere. But when the stratospheric temperature changes, it may coupled with the surface temperature through the QBO or convection cell or gravity wave, atmospheric waves. So this coupling may control the effect of the solar UV variation to the surface. The other is a plasma. Solar energetic particles or the substorm or geomagnetic storm particles can change the NO, nitric oxide in the stratosphere or mesosphere. And that changes the ozone. And when the ozone amount changes, the temperature in the stratosphere changes. And again, the coupling from the surface also changes. These are just models, ideas to connect the observed solar activity correlation with the surface temperature, but none of them are proven by quantitatively. So that is a challenging part of our SCO step and new Presto program. One of the Presto program is focusing on this topic. Okay, now let's go back to the plasma around the Earth. So the sun emits the plasma and it comes to the Earth. And as you know, the Earth is the permanent magnet, which has a N and S pole. So the magnetic field is like this. And the solar wind plasma from the sun hits the Earth. Then because of the space charge in the solar wind plasma, they can interact with the magnetic field and they can change the shape of the magnetic field. But they cannot move across the magnetic field line. So they cannot get into the Earth magnetic field region. This is so-called magnetosphere. So compared with the high density solar wind plasma, the magnetosphere is a low density. This is one particles per cubic centimeter. This is about 0.1 particles per 1 cubic centimeter. So this is a kind of bubbles, plasma bubble in the solar wind ocean. But some of the plasma can get into the, particularly in the magnetic tail region, and they can energized. And when they move along the magnetic field line, they hit the atmosphere and creates the aurora. So that's why we have aurora only at high latitude, not in the middle latitude, not at India, but only in the northern Russia or southern Antarctic region. So this is a summary view graph, schematic view. The sun is emitting the plasma to the Earth. Sometimes it causes the eruption, but the Earth is protected by the magnetic field. And because of the solar wind, the magnetic field shows the tail-like shape. And when the tail splits, then it hits the plasma to the Earth, and that is a Aurora activate, and that is the Aurora substorm, which I showed before. Okay, I repeat it again. The sun emits the plasma, and then it hits the Earth, and the tail becomes stretched, and sometimes it is disrupted, and disrupted by the magnetic field tension force. It is accelerated plasma and hits the Earth. That causes the substorm. Okay, now I finish the first part, and then I talk about the nocturnal airglow at the second part. Okay, now the airglow. Airglow was known when the there's no light pollution in the 100, 200 years ago. There's no artificial light. Then the people are more familiar to the air glow, because if there's no city light, you can see the mountain boundary of the mountain, boundary of the between mountain and the sky. That is mainly because of the air glow emission. The sky emits weak light, which is subvisual. So you can actually see the air glow, but because the air glow is a very dimming structure, so you cannot recognize it. But when you see the mountains, you can recognize at the boundary as the air glow. And as I showed before, in the space stations, we can see the air glow. This is Aurora, but as the space station gets into the lower latitude, the Aurora disappears, but still you can see the green emission just above the horizon. This is air glow. So air glow covers all the Earth like this. So the air glow emission height is typically 80 to 300 kilometers, which is the region where the ionosphere exists. Atmosphere becomes plasma, which is called ionosphere. And this region is also the region where the space shuttle, International Space Station or satellite is flying. And the most common air glow features are seen in the 80 to 100 kilometers from the oxygen green light emission, nitrogen yellow emission, and hydroxyl infrared emission. The other intense emission is from the oxygen 630 nanometer, which is the red emission coming from the 20 to 30 kilometers. And this region in the bottom side, air glow, it is a mesosphere, top side of the mesosphere. And the upper part of the air glow, it is a bottom side of the F-layer ionosphere. And actually, this red emission is proportional to the ionospheric plasma density. So using this red emission of the 630 nanometer, you can visualize the disturbances of the ionosphere. Now, this region is mainly disturbed by the waves from the lower altitude. For example, the gravity waves are caused by the tropospheric convection that propagate upward, and sometimes, most frequently, they broken in the mesopause region, and momentum release occurs. And secondary waves comes up, and eventually they can initiate the ionospheric Rayleigh type instabilities. So we can see these kind of waves or instabilities using this oxygen red line emissions. Like this. This is all sky images of the mesospheric gravity waves or oxygen ionospheric plasma. So first, most distinct structure in the 630 nanometer air glow in the ionosphere is plasma bubbles, which can be also observed in India. This is all sky images of the plasma bubble observed at Sata, Japan, which is the southern edge of Japan. You see at night, the star is moving, and after the midnight, you see the dark shadow is moving from west to east. Again, the star is moving to the westward, and the dark shadow coming to the from west to the east. And this dark shadow is called plasma bubble, because dark region means low density of the plasma, because the this emission intensity is proportional to the plasma density. So this tree-like structure is where the density is missing, low density. So that's why we call this as a plasma bubble. And if you measure this plasma bubble at two stations in southern part of Japan and northern part of Australia, we eventually see that this structure is symmetric between the northern and southern hemisphere. It's completely symmetric like this. So this means that this plasma bubble structure is along the geomagnetic field line and growing at the geomagnetic equator upward, and it is mapped to the northern hemisphere and southern hemisphere. And nowadays, we know the mechanisms to create the plasma bubbles, which is basically the Rayleigh-Taylor type instability. Let's think about the ionosphere. In the equatorial ionosphere, the ionospheric current is mainly moving eastward, mainly because of the gravitational force, and magnetic field is horizontal. And if there is a small perturbation of the bottom side of the ionosphere, there is a less conductivity at this region. So because of this electric current cannot flow in this region. You have a positive charge here, a negative space charge here. That creates the eastward electric field. And this eastward electric field and the background northward magnetic field, that creates so-called E cross B drift of the plasma, which is E cross B direction is upward. So when the small perturbation happens, then that plasma start to move upward. And that means that grows upward, and creates the plasma bubbles, which is a void region of the plasma in the equatorial ionosphere. That's why we see this kind of symmetric structure in the northern and southern hemisphere, and that grows from the equator. And the important thing of the plasma bubble is that that interrupts the satellite to ground signal, radio signal. This is a GPS radio signal intensity, which is used to make a positioning, GNSS positioning or car navigation. And when the plasma bubble starts to appear in the sky, you see the radio wave intensity was highly disturbed and weakened. This is called scintillation. So that means when the plasma bubble appears above the sky, we cannot communicate with the GPS satellite. So we cannot use the car navigation. We cannot use the satellite TV. So that can be a serious issue, particularly in the equatorial region of the Earth. So we are trying to understand how, when, where the plasma bubble happens, and try to make a prediction of that plasma bubble. That is one of the SCOSTEP Presto program is aiming for, and Dr. Paramraju is the co-leader of this project. And the other major disturbance in the ionosphere is so-called traveling ionospheric disturbances, TIDs. This is a composite figure of the airglow images obtained at 5 ground stations in Japan. And we take airglow images at these stations and make composite images at these stations. This is a 630 nanometer airglow emission, which is proportional to the plasma density in the ionosphere. And as you can see, there's a northwest to southeast structure, wave-like structure moving southwestward. This is a typical medium-scale traveling ionospheric disturbance, so-called MSTIDs. And interestingly, in summertime, almost all night, we see this kind of structure over Japan. At middle latitude, it is very frequently observed. So this is a common phenomena at middle latitude ionosphere. And interestingly, we see the similar structure in both Sata in southern part of Japan and Darwin in the northern part of Australia. And so when we map this structure image of the TID to the conjugate station, we see the very similar structure between the two stations. So if we combine these two images, you can see the phase front fit clearly at these very different, about 5,000 kilometers away. But this 50 kilometer small scale structure propagate to 5,000 kilometers. This is another example between the Shigaraki, Japan, and Rena Springs in the desert of the Australia. And top part is the Shigaraki airglow images, and bottom part is the Renner Springs. And you see there's a clear one-to-one correspondence between the two structures. So clearly, this 50 kilometer or 30 kilometer structure is mapping to more than 1,000 kilometers, more than 5,000 kilometers. So again, this indicates the electric field coupling between the northern and the southern hemisphere, similarly to the plasma bubbles. And this indicates that that MSTID structures in the northern hemisphere is mapped to the southern hemisphere. And we also find there's a corresponding structure in the E region ionosphere. So there are 4 layers in the northern and southern hemisphere, and they are electromagnetically coupling each other. And probably there must be a field line current and pointing flux. That is a very interesting point of the hemispheric coupling of the ionosphere. This is another interesting image obtained at Shigaraki, Japan. Here, the medium-scale traveling ionospheric disturbance is moving southwestward. But in the bottom side, which is the southern part of the sky, there's a plasma bubbles. And plasma bubble is moving eastward, and the MSTID over Japan is moving southwestward. And they collide each other. You see, they collide each other in the southern part of Japan. Then the plasma bubble disappears, and MSTID survives. So in this case, the MSTID is stronger than the plasma bubbles. That is the interesting electromagnetic coupling in the middle latitude ionosphere, indicates how the plasma instability couples each other. This is another interesting example in the northern part of the Earth at high latitude. We see the medium-scale traveling ionospheric disturbances here. This is an image at Tromsø in the Norway, near the Aurora zone. In the northern sky, you can see northern edge of the sky. You can see the Aurora. This is the Aurora, and in the southern part of the sky, you can see the MSTID, medium-scale traveling ionospheric disturbances. And as you see, the MSTID oscillate like this all together. On the 4 images, it oscillates, and that oscillation seems to coincide with the brightening of the aurora. So if you see it in details, the MSTID oscillates like this, and brightening of aurora happens. Then we convert this all-star image into the geographical mapping in latitude and longitude, and we cut the this image in this direction to see the longitudinal motion. The vertical axis is the longitude, and horizontal axis is the time from 15 to 19 UT. And as you see here, the whole structure is moving eastward. Then it suddenly oscillates and goes back. And at this timing, if we take a vertical cross section, north-south cross section in this plot, this is the second panel shows the north-south cross section. The top part is north and bottom part is south. And this is the auroral airglow intensity. And at this timing, when the structure oscillates, the northern sky, the aurora brightens and start to expand to equator. And in the bottom panel, this is a magnetic field structure in Tromsø and nearby stations. And at this oscillation timing, there are small magnetic field perturbations. So clearly, this indicates that this MSTID, medium-scale traveling ionospheric disturbances, are affected by the auroral disturbances and probably by the electric field propagating from high latitude to low latitude. And that causes the oscillation of the MSTIDs. And another traveling ionospheric disturbance is the so-called large-scale traveling ionospheric disturbances. This is one example during the geomagnetic storm observed at Rikubetsu, northern part of Japan. Again, this is a 630 nanometer. And as you see, the 630 nanometer emission enhanced in the northern sky, and the big blob, big structure move southward. This is much larger than the previous medium scale traveling ionospheric disturbances. That's why we call it the large scale traveling ionospheric disturbances. And that kind of structure can be also visualized by the GNSS multi-point measurement. This is a figure of the GNSS satellite. As you know, the GPS satellite, GNSS satellite, the satellite emits the radio emission and the receiver receives it. And because the radio wave propagates in the ionosphere, and the radio wave causes delay of the depending on the amount of the ionospheric plasma density, we can measure the line of sight density of the plasma using this receiver. And in Japan, we have so many, more than 1,000 receivers. So we can visualize the plasma density of the ionosphere over Japan like this. And this data can be obtained every 30 seconds. Then we see the big enhancement of the plasma density propagate southward. And another enhancement of the plasma density propagate southward. This is again the large scale traveling ionospheric disturbances. This is observed during geomagnetic storms. And this is understood as the auroral disturbances during geomagnetic storms causes the heating of the atmosphere. And heated atmosphere propagate like a tsunami to the equatorward and causes the so-called traveling ionospheric disturbance, large scale traveling ionospheric disturbances. So this kind of phenomena is often observed in the geomagnetic storms. And the airglow emission can be also observed from space. This is one example of the UV, ultraviolet airglow emission, which is also proportional to the plasma density in the ionosphere from space by the image satellite. Recently, the gold satellite make more detailed structure. But anyway, from the space, you can see the two belt of the high density plasma. Except for the auroral region, there's another two belt, particularly in the equatorial part of the ionosphere, which is the so-called equatorial anomaly. And if we continuously take this image and make averaging of the airglow structure, then they found that interesting enhancement of the airglow above the South America, above Hawaii, above Asia, and above Africa. This is so-called wave number 4 structure. And this indicates that the land-ocean structure and the associated atmospheric disturbances propagate to the ionospheric altitude around 400 kilometers and controls this airglow and plasma density structures. So these are the structures what we see in the ionosphere using the airglow. So we see the plasma bubbles or various ionospheric disturbances and aurora. And they are caused by the solar eruption and high energy plasma, and aurora causes ionospheric disturbances. And they also control the plasma bubbles in addition to the atmospheric waves. And they affect to the GNSS positioning or radio communication or satellite anomaly orbital changes. So these structures are also related to the human activity in space and the space use by the human beings. So this predictability is another big issue for the SCOSTEP-PRESTO program. And Param Raju is one of the leader of this project. So in summary, aurora appears around the altitude of the 90 to 600 kilometers, where the International Space Station and satellite are flying. And aurora grows due to collision of space plasma with the Earth's atmosphere. The space plasma originally come from the sun and from the Earth's atmosphere. They are stored and energized in the Earth's magnetosphere. We can visualize various space plasma dynamics through Aurora. And we can also visualize dynamics of the upper atmosphere, like plasma bubbles and turbulent disturbances through airglow. And the space plasma and upper atmospheric dynamics often causes satellite anomaly, satellite positioning error, or radiation dose of that astronauts, ozone destruction, and it's so-called space weather or space climate effect. That's why we are studying this aurora and airglow and upper atmosphere space around the Earth. Okay, that's it. Thank you very much.
Thank you, Professor Shiokawa, for this nice and illustrative talk with several interesting movies, which are actual data that you have shown, and I think you have nicely shown several pertinent solar terrestrial problems that can be addressed by monitoring or looking at airglow and aurora at different locations. You nicely blended these issues, and I will now, probably will take some questions. I will now invite my colleague, Dr. Lokesh Sahu, to first go through the questions on the chat box. Then probably we'll come to the panel members here. Yes, Dr. Lokesh.
Yes. Thank you, Professor Shiokawa, for being with us. And now we'll start the interaction sections, as mentioned by Professor Raju. And first, I will read the questions posted in YouTube chat box. Yeah, so if you have any difficulty in understanding my pronunciation, you may please ask to repeat. So a question is, one question from Shubir Mandal is that, are the emission altitude widths and peak emission altitudes for aurora similar to airglow emissions?
Actually, the emission altitude changes depending on the intensity of the precipitation of the particles. The red line emission in aurora is mostly around 200 kilometers, and green line emission on aurora is mostly around 100 to 150 kilometers. But in case of airglow, it is rather fixed. As I showed before, it is more like green line is 90 to 100 kilometer, and red line is 200 to 300 kilometer. So aurora altitude is more controlled by different depending on the precipitating particle energies.
Okay, thank you. And we have another question from Ankit Kumar. His question is, are the structure of aurora different above and below the International Space Station?
We are looking at the same structure from ISS or from ground. So the structure should be same, but of course, depending on the looking angle, you may see differently, but the actual structure should be the same. But by looking from the International Space Station, we can see the kind of altitude profile more clearly than from the ground stations. So actually, from space, you can estimate the height profile of the emissions with the accuracy of several kilometers or less than several kilometers. So space measurement has an advantage to see the altitude profile of the structures.
Thank you. We have another question from Mr. Ankit Kumar. This question is the simultaneous observations of aurora and airglow possible? With a note that airglow presents all time, but aurora does not.
Yeah, aurora is also always appears, but it is limited in the high latitude. So And Aurora emission, the green line emission and red line emission of the Aurora is exactly at the same wavelengths of the airglow emission. Actually, the same atmosphere, I mean, oxygen atom emits the green line and red line. The difference is excitation mechanisms. One is the Aurora is caused by electrons, but the airglow is caused from a chemical reaction energized from the solar UV emission. So if the Aurora and the airglow appears simultaneously in the same place, we cannot distinguish them because auroral intensity is about 10 to 100 times stronger than the airglow emission. So usually Aurora masks airglow emission.
Okay. So there is a question from Mr. Sohan Saha. His question is, Aurora emission altitudes are between 90 to 600 kilometer. And his question is, what are the emissions found above a flare peak height?
Yeah, let's see. Most of the auroral emission is coming from the bottom side of the flare, but some emissions may come from high altitude, like 8446 from the oxygen, and 777 is a similar profile to the ionospheric density profile. So maybe 8446 or 777 is at high altitude. And also the 630 nanometer, in case of SAR arc, particular auroral arc at the subauroral latitude, they are coming from 400 kilometers. So in that case, they are in the top side of the ionosphere.
Okay. So another related question is, how can we differentiate between aurora and airglow at high latitudes if both emissions are coming from same altitude, 90 to 300 kilometers?
Yes, yes. So as I said before, we cannot distinguish if they appear simultaneously together. But aurora emission is 10 to 100 times stronger than airglow emission. So when the aurora appears, airglow cannot be observed or mixed together.
Another question is, can interaction of MSTID and plasma bubble change the F region plasma distribution at interaction location or anywhere?
That's a good question. As you see, in the collision of the plasma bubble and MSTID disappears. The disappearance means the plasma bubble disappears. Plasma bubble disappearance means plasma bubble is void of the density. The disappearance of it means the plasma density is filled. Plasma bubble is filled by the plasma. And probably it is caused, the filling is caused by the ecrospeed drift electric field inside of the MSTID. You know, the MSTID is accompanied by the electric field, oscillating electric fields, and that causes the ecrospeed drift of the plasma. That pushes plasma into the plasma bubble. That fills the plasma bubble and causes the disappearance of the plasma bubble. That is our understanding. But the opposite, the question is the opposite can happen. The plasma bubble is also affected, is accompanied by the electric field. So that electric field can fill the MSTID, and the MSTID disappearance can also happen. But for this particular case, the electric field in the MSTID fills the plasma bubble void density.
Thank you. We have a question from Mr. Sohan Saha. His question is, what is the difference between the generation mechanisms of MSTIDs and LSTIDs?
Okay. MSTID and LSTID, the differentiation is purely by the scale size. Typically, we call the LSTI large-scale traveling ionospheric disturbance as a scale size more than 1,000 kilometer. And scale size less than 1,000 kilometer, we call it a medium scale. And large-scale traveling ionospheric disturbance is most likely caused by the atmospheric waves. The major cause of the atmospheric wave is Aurora. On the other hand, medium-scale traveling ionospheric disturbances, in these cases I showed in the examples, they are accompanied by the electric field. So that means they are caused by the plasma instability. But there are another group of evidences that shows that these MSTIDs are caused by atmospheric waves, gravity waves. So in that sense, the large-scale traveling ionospheric disturbance, this is also atmospheric gravity waves. So both atmospheric gravity waves can create large-scale or medium-scale traveling ionospheric disturbances. And in addition to that, the plasma instability can also create medium-scale traveling ionospheric disturbances, particularly at the middle latitude.
Yeah, thank you. We have another question from Dr. Subir Mandal. This question is, why the plasma bubble observed over Darwin showing more contrast compared to that observed in the conjugate location, SATA?
Yeah, that is interesting point. Possibly because of the slight difference of the locations, Darwin is a little bit lower latitude than SATA. So Darwin is closer, little bit close to the plasma bubble compared with SATA. So if we shift the SATA station to bit lower latitude, probably we can see more contrast structure. The other point is that the background plasma density can be different between the northern and southern hemisphere. Possibly that in Darwin, at that time, we have a stronger airglow intensity because of the background density is high. And maybe you have a lower plasma density at SATA. That makes a difference of the contrast.
Okay, so we have kind of last question from YouTube chat box, and the question is from Mr. Pradeep Suryavanshi. His question is it possible to predict the plasma bubble in advance? If yes, how much time before?
That's a very good question. That's what we are trying to make. This kind of plasma instability is mainly controlled by the height variation of the ionosphere. This instability easily occurs when the ionospheric height is high. And when the ionospheric altitude is low, this instability is stabilized, so we don't have it. So if you can predict the ionospheric height, we can predict the plasma bubble. And the ionospheric height is most high at the evening time after the sunset because of the conductivity difference between daytime and nighttime. You have a high plasma, high ionospheric altitude. And that is also dependent on seasons. So that seasonal variation of plasma bubble is well known, and that was also reproduced by the global TI GCM, global circulation models. So using the global circulation models, we can make a prediction of the seasonal variation of the plasma bubble. However, for example, the plasma bubble is frequently occur in March and September equinoxes. And solstice time, we don't have much plasma bubbles. However, in the equinox time in March and September, there is a clear, significant day-to-day variability in the plasma bubble occurrence. Even in the March time, one day we have a plasma bubble, next day we don't have plasma bubble, and next day we have a plasma bubble, and next day we don't have plasma bubble. So there's a significant day-to-day variability. That day-to-day variability is difficult to predict. And recent study suggests that day-to-day variability has a good correlation with the geomagnetic activity. When the activity becomes high, I think it is suppressed. The plasma bubble is suppressed, like that. So, and that is a weak point for the GCM model. Global GCM model can make a seasonal variation, but cannot make a day-to-day variability. But that is that depends on the difficulty how the geomagnetic disturbance is included in the GCM model. So if we can parameterize the auroral energy input into the GCM model, possibly we can make a better prediction of the day-to-day variability of the plasma bubble occurrence. That is one thing we are now challenging. The other thing is after the plasma bubble occurs, we know that they propagate eastward, so continuously during the nighttime. So if we know we know that the plasma bubble took place in the west, then in the eastern station we can see it. For example, if you see plasma bubble is occurring in African continent, maybe some hours later, India will observe the plasma bubble. So in such a case, we can make a plasma bubble prediction about maybe 1 hour or 2 hours before it comes to your longitude. That is possible.
Thank you. So we have a last question.
Yeah.
We'll take last question from the YouTube chat box. The question is from Dr. Kuldeep Pandey. This question is, can there be differential auroral heating in the northern and southern hemispheres? In such cases, how will it be possible to get the dominated side of MSTIDs?
Yeah, auroral heating creates a large scale traveling LSTIDs. So anyway, yeah. Yes, the northern and southern hemisphere can have a differential heating. Basically, the aurora is symmetric between the two hemispheres, but actually, for example, the magnetic field intensity is different between the northern and southern hemispheres slightly, and the geomagnetic pole is slightly different from the geographic pole. So that creates the difference in the northern and southern hemispheres. So the auroral heating energy input can be different between northern and southern hemispheres. So in that case, it's difficult. Maybe you can use the geomagnetic field variations in the northern and southern hemisphere observed, which is the most available data on global scale. Then maybe you can estimate which part is more strong about the auroral heating.
Okay. Thank you, Professor Shiokawa. Now it's time to, I request our colleagues who have joined in WebEx panel to interact with Professor Shiokawa. So I request my colleagues if they have any questions.
Yes, Kazuo, I think I have one question, a couple of questions though, but and when you are, it's very nice to see the conjugacy both in Aurora and in the Darwin SATA data. Okay, I'm curious to know, are you, did you get any occasions when you don't see any conjugacy, and if so, what could be the reasons? Because these are nice pictures when you say conjugacy.
In MSTID, you mean?
Yeah, or MSTD or the plasma bubble, for example. What you are showing, the Darwin and SATA. It's very interesting and expected image. It's very impressive though. But I'm just asking, are there instances when you don't see conjugacy?
For MSTID in Japan and Australia, almost all cases we see the conjugacy.
Even in the
when
plasma
the data is
bubble,
available.
when plasma bubble formation also.
Plasma bubble is also almost all cases. When both data from both stations are available, we see the conjugacy. The one case which we do not see the conjugacy, which is between Indonesia and Thailand, it's lower latitude conjugate stations. We see non-conjugacy for the so-called brightness wave, which is a common wave, large-scale TID, propagating away from the equator around the midnight, related to the midnight temperature maximum. And we observe such kind of forward moving wave over Indonesian station. However, in the conjugate station in Thailand, we do not see anything. So that means the non-conjugacy, and that is explained that these large-scale traveling atmospheric disturbance can be caused by the neutral atmospheric oscillation because of the midnight temperature maximum. So like a large-scale TID. In that case, you don't expect the conjugacy because it is a neutral oscillation.
Yes. Okay. Just one last question from my side, and that is regarding one of the nice example that you have shown in terms of the plasma bubble getting disappeared when the MSTID happens.
Yeah.
And again, the contrary. Yes. So the contrary examples. Do you have any evidence of the other thing happening, like if bubble sustains, but then the MSTAD gets disrupted when these two merge? Yeah.
Not much. No. This is very rare case.
I understand.
We see the plasma bubbles and MSTID together.
Yes.
We have another case that large scale traveling atmospheric disturbances interact with the MSTID, and then the interact with the plasma bubbles.
Yes.
And at that time, the plasma bubble again disappeared.
Okay. Yes.
Thank you.
Fine. Thank you very much, and enjoyed your talk. Okay, over to you, Lokesh.
Thank you.
Yeah. One of our colleagues, Professor Debanti Chakravarti, would like to interact with you. Yeah, Deepu, please.
Kazuo, I have a couple of two small questions.
Yes.
The first question is that by looking at the orbital feature on the night side, is it always very easy or complex to understand the magnetotail plasma dynamics?
Magnetotail plasma dynamics?
Yes.
Nowadays, we have many satellites in the magnetotail, like geotail or Themis satellite, or in the Magnetosphere, RSA or RBSP. So using these, it's still a point observation, but we can, this cartoon was written based on these satellite measurements. So for example, we can see the strong earthward plasma flow. That is evidence of this reconnection. And earthward plasma flow, there's a location where the plasma flow reverses from earthward to tailward, statistically. So using that, we can speculate that this reconnection location is mostly occurring at 20 to 30 Earth radius on average. And using the magnetic field measurement at one point, we can see whether this magnetic tail is stretched or now moving toward the Earth. Because when the magnetic field is moving toward the Earth, the magnetic field becomes more dipole-like. So the local magnetic field becomes more dipole-like. That indicates the dipolarization and earthward flow. So in such a way, even on stations, we can speculate what's happening in the tail.
Yeah, thank you. And the second question is that generally we associate LSTIDs with geomagnetic storm.
Yeah.
But do you see any instances when MSTIDs are causally connected? The generation of MSTIDs are causally connected with the storm event? Or is it possible? Because you showed one example where magnetic field actually is affecting the sudden vibrations in the MSTID features captured by the images.
Yeah. these storm time phenomena is caused by the mainly auroral heating, and large scale structure can survive long distance. So we can observe it in Japan. And small scale structure cannot survive for long distance. But if you get closer to the aurora, you can see small scale atmospheric waves, possibly caused by auroral energy input. That can be MSTID. And actually, using the IceCat radar, they do observe the oscillating gravity waves associated with auroral substorms, which is a small scale, medium scale disturbances with aurora. So I think the auroral heating itself has a small scale structures because aurora has a small scale structures. So if you get closer to the aurora, you can expect such a small scale structures. But if you are away from the aurora, such a small scale gravity wave cannot survive, cannot propagate such a long distance, and only the large scale structure can survive to reach to the middle latitude.
Thank you so much, Kazuo. Thank you. Enjoyed the talk.
Thank you. Thank you. So the session is still open for our WebEx colleagues. So if they have questions, they can interact with Professor Shiokawa.
So, Lokesh, can I ask a question?
Yes, ma'am. Please go ahead.
Yeah, thanks, Kazuo, for a very interesting talk. I enjoyed listening to it. I have a very basic question. Like when we predict geomagnetic storms, we should know the southward component of the magnetic field and the velocity.
That's
In
right.
case of, and then we sort of predict when the storm will occur and what will be its intensity. So in case of aurora forecast models, you need an additional output like the location of the occurrence of auroras also. So what is the status of the model of aurora forecast? Which parameter is predicted well compared to the others?
Most of these tail structures outside of the maybe geosynchronous orbit can be described by the magnetohydrodynamics approximation. So outside of 6RE, probably you can use the MHD simulation. And the MHD simulation is well described, except for the reconnection rate. You can adjust, make a resistivity in the reconnection region in the tail. But so in that sense, the substorm prediction is very difficult. But when the IMF becomes southward, in the MHD simulation, anyway, creates the substorm-like features, and that creates the energy input. The most difficult part is when the MHD approximation does not hold. Like in the inner Magnetosphere, radiation belt particles, they are not caused by the MHD processes, but caused by the wave particle interaction, which is a small scale wave particle interaction. So that cannot be included in the global simulation modeling. So radiation belt particles is still challenging. There are several attempts recently made to combine this inner Magnetospheric particular model, combine that with the MHD model, like a Bartras Shirashian semi model. They combine the MHD model with the inner Magnetosphere model. And the other part is the solar wind Magnetosphere interaction, but that was already well described by the MHD because the solar wind is MHD, Magnetosphere is MHD, so that's easy. The other part is the interaction with the ionosphere. Now, several models also establish the conductivity modeling of the ionosphere and connect it to the feedback to the MHD model. So many cases, this inner Magnetosphere and the MHD model also contains the ionospheric conductivity model. But if you want to understand the atmospheric heating and their effect to the LSTID or plasma bubbles, then you need to combine these models with the atmospheric GCM. That kind of attempt is recently done by US teams like TIGCM and global MHD models. But it's still challenging. And also another attempt is necessary for the chemical parameters like ozone decrease or NO, nitric oxide, which is affecting to the long-term variation of the climate change, like a particle effect to the climate change. That is really challenging and not done yet.
Okay. Thank you.
So the boundary part is always challenging.
Challenging. Yes,
Yeah.
that's what I expected.
Macro scale, micro scale coupling is always challenging.
Thank you. So we can continue our interaction for a couple of minutes. So if our viewers in WebEx they want to interact, please welcome. So yes, so I think we have come close to the interaction sections, and thank you, Professor Shiokawa, for
Thank you very much.
for very nice talk and taking questions and interacting with our viewers. Now I hand over the session to Professor Deepalam Raju for further proceedings.
Yeah, I think yeah, it was very nice to have you, Kazuo, and then it was very interesting talk, as I said, with various examples, various movies, showing it very nicely, various aspects. And, thank you very much. And if I think I'll ask Durga Prasad, Dr. Durga Prasad is there.
Thank you, Professor Pallam Raju, for giving me this opportunity to get the vote of thanks. Thank you, Professor Shiokawa. On behalf of PRL Amrut Vyakhyaan Committee and entire PRL family, I thank you for accepting our invitation and delivering the 9th Vyakhyaan of this 75 episode PRL Amrut Vyakhyaan series. So thank you for your informative, wonderful, and a very colorful Vyakhyaan and patiently answering all the queries posed by our YouTube viewers as well as the panel members. Thank you very much. I thank Professor Anil Bhardwaj, Director, PRL, for his constant support and encouragement to keep this series going on. I thank Professor Pallam Raju, Dean PRL, for introducing the speaker and also giving all of us an opportunity to listen to an enlightening Vyakhyaan. I thank Professor Nandita, Chair, and Dr. Lokesh, Co-Chair, and all the members of Amrut Vyakhyaan Committee and all others behind for their constant efforts. Last but most important, I would like to thank all of our participants and viewers who have joined us live through WebEx and YouTube platforms today for this Vyakhyaan. So with this, we come to the end of this episode of PRL Ka Amrut Vyakhyaan and sign off for today. See you all next week with a new and interesting Vyakhyaan. Till then, stay tuned.